So my name's Konstantin Worms. I work at AWS as a solution architect on the M&E team. And the topic for today is, I'm going to talk about Amazon AI, deep learning, and how this can be applied to media workloads, specifically for AWS. So I'm not really here to try and make anyone use a product. This is more of an educational experience, if you will. So I'm sort of going to walk through, after an intro, I'm going to walk through how some of our customers are building AI and ML and deep learning solutions on top of AWS for their specific media use cases, and those are quite varied. So anything from analytics to VOD to live OTT, a lot of the common things that you're all familiar with, but also some interesting niche use cases, right, like human trafficking, etc. So there's some interesting things there. And really, just to get started, like I said, I'll do a brief intro, just in terms of how we interoperate and how at least AI has been used at Amazon, and then start moving up the stack. So in other words, from the core building blocks that you can use to build your own deep learning solutions for different use cases, up to managed service type solutions. So things where you don't have to build the infrastructure, maybe you want to do labeling, facial recognition, etc. And then what that looks from an actual use case example, what the architecture looks like, what the use cases people are building out. Many of you are probably familiar with things like Alexa, but there's some other things here outside of the Amazon proper website, for example. And there are a lot of different aspects here where different types of, say, AI, ML, deep learning are applied. So, if you look at the Kiva robots for fulfillment centers, there's obviously computer vision applied there, right? There's machine learning for things like optimizing routes, etc. If you look at things like other products that we work on around AWS or our customers, computer vision is something there. If you look at, for example, Alexa and then the actual services that we offer for people to build their own, say, chatbots or speech-to-text, text-to-speech type services, things like Polly and Lex. These are like natural offshoots of a lot of the technology that we have. And then the interesting one is, when you start combining these, like you combine, say, computer vision with machine learning and deep learning, then you have things like Amazon Go, right? So this is where you can walk into a store, basically take items off the shelf and walk out without going through a teller or a checkout, right? So those are scanned computer visions used to track them, etc. And that sort of covers, a lot of just outside of AWS, all of the other Amazon entities as well. So, if you look at the net combination of all of that, we have, thousands of employees in all these different niche areas focused specifically on different kinds of AI workloads, tooling, etc., not just media. And I think the important thing there is that all of these media workloads and these types of solutions that customers build actually benefit from these other use cases. This should be familiar, right? This is one of the newer Amazon offerings, the Alexa Show. But the reason I show this here is like, your next level FaceTime, if you will, is that this is like an orchestration of a secondary activity from speech recognition. So in other words, I now have a touchless device that I can use to make calls, but I'm using speech-to-text, natural language processing, etc. on the back end. And like I said, those technologies are also exposed in part through things like Lex and Polly for people to build their own services. And then if we look at other things, right, like going back to, say, traditional media, like example here is X-Ray, which is a service for Amazon Video that gives you, whenever you pause a video, it gives you the actors, maybe details about it. If you look at the other apps that, say, are not, primary screen-based, maybe secondary screen, like, say, an iOS device, this is where more important or interesting things get introduced into this type of workflow, if you will. So things like Not only how do we identify actors when we pause the video at a certain point in time through, say, IMDb and facial recognition as one example of how that could be done, but also how do we actually do things like topic modeling? So like consider all of the closed captions. What if I have a whole bunch of, say, content, and I want to model the actual themes or the thematic type of use cases around that content? And it goes beyond traditional theatrical type content. So if you think of things like political sentiment, et cetera, natural language modeling for different segments of programs, you can see where that can then be used for other things, right? So we could look at, say, media encoding based on a genre, but what if we looked at media encoding based on segment and topic extraction, because there may be multiple genres across a single, say, feature film, if you will. So this is, just another example of what people are building, right? So we did this thing, or at least the NASA folks built this out. And this actually runs in a browser. You can find this online. It's using Alexa. So, the back end is actually powered through Lex and Poly, promoted as that. But essentially, the way this works is when you do a recording in the browser, it's using open source frameworks for WebRTC, capturing the audio, shipping that back to Lex, which is doing the natural language processing and speech recognition, and then that's returning you whatever the question that you asked. So I apologize, I don't think the sound will work on this. Oh, there we go. So, this is twofold in terms of the data that gets returned. Now, the reason I show this is I'm not going to get into Lex and Poly. I'll show where they sit, but, that would draw this out to another hour to 2 hours or so. So I'm focusing more on image, deep learning, recognition, et cetera. But the interesting thing here is that there's a vast array of languages. There's a W3C standard for SSML, which is a markup language for speech. So that lets me do things like slow down, add whisper, and it basically gives a more natural version to whatever the speech is that's been fed back to me as I synthesize that. So at least if we look at adoption of AI for media on AWS, a lot of these are actually, and some of these I got from Streaming Media Magazine, but the amount of internet users, the amount of photos that people are taking, I thought the interesting stat was you'll never take less photos in the current year than the previous year. So people are always going to consume and take more photographic media. And that becomes a challenge for classifying it, right? So we then look at, in terms of utilization on AWS, media customers. It's not uncommon to have, say, multi-petabyte asset storage for, say, supply chain, et cetera. And in some cases, we're seeing customers that do greater than 1 petabyte a month of ingest, continuous. So month over month, they're pushing in 1 petabyte. It's not a one-time move of their content library. So why AI in the cloud? So the big thing, of course, here is that it takes a lot of GPU, CPU horsepower to train the models that are used to do inference to be able to tell me, X, Y, or Z, this image is a cat, for example. So from that perspective, there are a lot of things on AWS that are a good fit for that, not only for just processing media, but things like potentially GPU, CPU, and FPGAs, where there's probably a considerable capital investment to actually have that running on-prem. Plus, you can consume these only for the time that you need to, say, do training. So I'll get into that as well, just the time constraints around that. But at least on AWS, we have this notion of per second billing and spot, which is basically spare capacity that you can get for, say, up to 90% off of the on-demand pricing of compute. So these two things, specifically the storage that is attached to the instances and the VMs that you spin up to do, say, the deep learning, that is very intensive, right, you can take advantage of these two constructs to basically reduce the cost there. So we see a lot of local training. So data scientists will do their training on-prem. They may have a NVIDIA cluster. They may have a bunch of 1080 Ti's, for example, or actually maybe server-level GPUs, if you will, like V100s or P100s. But essentially, the local training then gets deployed to the cloud for those lengthy training sessions that could require either a lot of compute for a short amount of time or cheaper compute for a slightly longer amount of time. So there are a couple of key use cases that we see as well. And some of these are pretty self-evident, right? So metadata enrichment. So if I can identify all the objects in a scene, I can then use that as my first level of adding, say, asset tags to new items arriving in my supply chain and my asset management system. There are other things like automated editing. So here, things like if I can identify the objects in a scene, and I can then tie that to a low-resolution proxy, I don't have the ability to do, say, MD5 hash against the two of those because the checksums don't match. How can I make sure that my original content, let's say, gets ingested a couple days after I've generated a low-resolution proxy? How can I match the two of those up? So there are things like perceptual hashing, et cetera, as one option, but object detection and then figuring out where the objects appear in the scene and then generating a hash over the net sum of that is another way to accomplish that. We also know that things like B-roll, for example, right? B-roll may be the A-roll. That may be the content that we actually want to use. So the ability to just automate and tag that as it arrives actually lets us put those into different buckets, and then editors can easily retrieve additional footage. And then finally, security and analytics. So we see a lot here from the analytics perspective. For like smaller and larger studios, like maybe it's a 3D rendering house, for example, or 2D editing, where they have a lot of people working on different jobs, and this actually factors more into machine learning as opposed to deep learning. But essentially, they're looking at this as a way to try and predict how many, say, staff they're going to need for a job based on the past history of the performance of the different people on staff. So that way they can get enough people ready to go when they land the content and have to produce a shot, for example. And just, to break this down, right, I've been talking a lot about AI and ML and deep learning. There's a natural progression, from the 50s all the way through current. But there was a sort of an inflection point in around 2010, 2009-ish. Specifically with ImageNet and all the effort around that. I'll talk a little bit about that. But I think that just the basic thing for anyone that's not familiar with deep learning and machine learning and AI, these are natural building blocks, and they sort of fit into each other in this fashion here. So deep learning is a subset of the other two. And then if we look at media segments, right, so I talked about a couple of examples. So this sort of lays everything out glass to glass, right, from acquisition all the way down to, say, OTT delivery. I apologize that the gray is a little hard to read. But, if we look at acquisition, right, so there may be pre-processing and optimization we can do through ML and deep learning. A lot of the things that we're seeing now are the blue boxes, right? So, for example, enhancing digital supply chain with automated tagging on ingest, as well as things like live to VOD. When the VOD clips land on, say, S3 on Object Store, we can generate an event, call a managed service, and generate tags for everything that appears in there as objects. And then obviously things like analytics as well. So those are the fairly big plays there. And then I think the other thing that people don't realize is if you look across the whole AI ecosystem or that whole scape, if you will, there are actually quite a few customers, and many of these logos probably look familiar. But many people don't realize how many customers that we have are actually running AI workloads almost in some cases as primary workloads, not as augmentation, if you will, on top of AWS. So that's sort of the intro, right? So the whole thing now is where would we start if we wanted to build something? So we have to start with a use case, and this is a good one. So this is a real challenge, right? In that, especially identifying if it's a Chihuahua or a Muffin, and these are very similar to each other. You can see that the big thing here is that the confidence that's detected, right, is a 99.2 for an animal, a dog, Chihuahua. That's valid, right? But we have a higher confidence for other things as well, like food, dessert, and muffins. So this is why I'm starting at the bottom, because in many cases, you can't rely on a managed service to actually do these kinds of very niche use cases. And there is a way to efficiently do this, but you do have to build the infrastructure to do that. So just the 10,000, and I forgot to ask, is anyone here involved in machine learning or deep learning or? No one. Man. Anyway, this is the 10,000 foot, right? So you can think of this, and this particular example is my raw data is a face, and the result, I want to compare it with another face, or I want to make sure that it identifies this with a label that says face, right? So same thing for cats, dogs, etc. And the way this works is just, a quick intro, is that I have a training set, and the training set comprises of different categories, and these are usually directories. So there'll be a directory for cats, dogs, etc. Each one of these directories I'd have maybe 10,000 to 100,000 different images of those specific things that I want to label as a cat. So different lighting conditions, different shapes, different colors, etc. Now, the way the training works is there are two things we know, which is the result that we know, and there's also the input that we know. But the center point is this unknown piece, right? And it's modeled to work like neurons in your brain, or perceptrons as they're called, right? So what do these things do? You usually have multiple layers. And you can see along the top, right? So the first layer may be concerned with just identifying in small sections of that photo, what are the different angles and lines, right? In like say an 8x8 or 16x16 segment of that, right? And then the second layer may actually start identifying more detailed functionality. So it may be an actual curve instead of a couple pixels. And then we actually move to higher level features, which are, say, identifying eyes or a nose, right? And you can see that the top right there, the training data has a whole bunch of different pictures of faces. But the net combination here of moving through this network and doing things like pooling features together, et cetera, having those 10,000 plus images in each category allows us to do these epochs and train the system in order to recognize that. And if we do it accurately and the actual model is built correctly, the neural network is built correctly, then over a course of, say, 30, 40, 50, maybe a couple days, maybe a month, we actually train the network to then identify these different objects using new data or validation data with a high probability. So the net result is you want to train something to give you the validation data at a high probability, like 90+%. So typically here, training data could be anywhere from 10,000 to 100 million images, depending on how accurate that you want that to be. The one thing here, and this slide, this is an NVIDIA slide, the learning algorithm is calculated here as 30 exaflops or 30 GPU days. But I think in the course of maybe a year, the new instances we have now, the V100s, the biggest V100 is, and I just scribbled it down here, it nets you 1 petaflop. So that means it's 8.3 GPU hours to do this training. Which through an on-demand instance is $24 an hour, and it's $200 to train this with that amount of data. So that is monumental steps every year that we're going on these types of training and networks. And really the things that this allows us to now do based on just using stuff on demand is create far more complex pipelines, if you will, that go beyond just identifying, say, objects. So there are a number of services here, managed services, right? So some of these, some of these might be a choice. So Amazon Machine Learning. There's Poly, which does lifelike speech that I talked about. There's Recognition, which does image recognition, facial recognition. I'll talk about that. There's also Amazon Lex, which is basically a conversational engine, if you will. So you can combine Lex and Poly to make things like chatbots, if you will. And then we have a deep learning army, and that's this core piece I was talking about, right? So this is where we've actually configured an army with all the popular frameworks. And an army is basically an Amazon machine instance. So you can think of it like a customized version of Linux that you can spin up on any instance you want. So when that army comes online, you have all of these frameworks like TensorFlow, et cetera, installed and ready to go. And then the interfacing is fairly simple, right? So across all of the services for AWS, we have SDKs and APIs covering everything from things like Android, iOS, all the way to a CLI, and in languages such as .NET, Node.js, PHP, Python, et cetera. So this actually lays out the stack I was talking about. And there are three things here, like I said, I'm focusing on. The one is the vision as opposed to speech and language, right? So how do we do image recognition, et cetera? And then the core building block, which is built around something like, say, the deep learning army that's then running on, say, GPU infrastructure. So this, you can think of this as the stack going from the bottom up as you move up to more, say, managed services. And there's complete flexibility here to consume whatever permutation of these you want. So from there, I'll just talk a little bit about this particular portion here. So I talked a little bit about the different types of instances. So Amazon has a lot of different instances. F1 is FPGA based. There's X1, which has a lot of CPU cores. G3, which is your traditional NVIDIA type GPU. And then you have things like P3, which are V100, which is the data center or server hyperscale, if you will, level GPU. So these are sort of the, you can see some of the stats on the right? The one I was talking about that hits a petaflop, that's a 16XL. So there are actually 8 GPUs in that instance that you fire up, 64 virtual CPUs, like regular CPU cores. The important thing is you have 14 gigabits of bandwidth to the block storage and 25 gigabits of network I/O. And that's important because if you can churn through images really fast and you have to get through, say, 10 plus million of them, the network bandwidth could be the thing that is the crippling piece, right, before you actually run out of GPU cycles. So these are basically the use cases, and you can see there's some examples for how you would use this. Hopefully I have time at the end, but I'll show a demo of a FPGA instance running 1,000 frames a second. So it's basically looking at images and analyzing every image in 1 millisecond and returning every object and the main object classified in the scene. So if we get to like 5, I'll just fire it up then. But why is this important, right? And this is the training time that you want to do this. And the training time is important because you don't want data scientists, you don't want your algorithms, you don't want the products that you're building to be constrained by time, even if you could step these, right? So maybe have one workload going and then people start working on the other one. The problem is a lot of these, a lot of services that you may look to build with us, one may be dependent on another, right? So they may be serialized in the way that they're, that you need to actually work with them to build a product. So if you look at the K80, that's 38 hours. Now it's reduced to 6 hours with a V100. So that's a massive improvement of a very short amount of time. So things like Moore's law, et cetera, almost stop being applicable in this use case. So this sort of breaks down what is available on that deep learning army that I talked about. So we put most of the frameworks on here. It already has things like NVIDIA, CUDA DNN for deep learning. And then you can see the frameworks at the bottom, such as TensorFlow, MXNet, Caffe. There's Intel acceleration, if it's like the AVX 512. That potentially gives you acceleration there too. Microsoft CNTK, and then Caffe 2. And those are all the popular ones. So it's a really good starting point to just have a data scientist put data on, put a model on, and then get going with that using Keras or Theano, any of those. So what does this look like from now we have this core piece of compute, right? And we actually want to build a system to classify images and then provide a service to a customer, right? So this is the important thing here. There's a ring, and this ring is a continuous, over time you may do things like version your data sets for say, deep learning. Maybe you add more labels, maybe you add more data, maybe you get more photographic data. But essentially, the key point here is that it's force-fed by the data scientist team, right? And then there's also a component for human-aided active learning. So many of these things in terms of those initial image sets I talked about, if you have 10,000 pictures of a cat, how are you going to initially establish that what we call ground truth? In many cases, if it's very specialized, like say it's specialized pieces of equipment for, say, engineering, in the field analytics or whatnot for an engineering company, these may be specialized where I need actual people to go off and do that for me. So I'll get to that as well. But essentially, there's an ingest mechanism, and there are AWS services for all of these that make a lot of sense, and they're a good fit. The nice thing is that for many of the media workflows that we deal with, the same type of services, if you will, so like say S3 for asset storage for VOD, or supply chain, etc. The same type of hydration to actually operate on those archives is identical for deep learning as it is to things like traditional media workflows and pipelines. So I'll talk about mechanical Turk, but then there are a number of other things here. Lambda is a key thing or a key factor to consider here, almost like a glue to orchestrate the framework. And for those that don't know, Lambda is basically, you can think of it as serverless code, right? So you provide a function to a scaffold, and then we actually provide the infrastructure behind it, and we let the code run and return results. So that means you don't have to manage any underlying instances. You just manage these Lambda functions in the cloud. And then for version control, S3 once again, traditional compute, like this is where your deep learning army would actually sit here to do the modeling and the training, etc. And then the results for that would be stored back in S3. And then finally, you come up to your customer. And the workload there may be, here's an image of a cat, tell me what the label is. It's a cat. That's a very simple example, but that's essentially what this breaks down to. So I wanted to talk at least just a little bit on this, just from customer perspective, how large the scale is getting. So Clemson University did NLP topic modeling, and they spun up over 1.1 million vCPUs, which I think is the current, say, world record for that amount of consumption. The important thing to bear in mind here is this was done in one region in US East, so it's not using multiple regions at AWS, and also using spot capacity, so spare capacity. So if you then look at 1.1 million vCPUs, consider if you were able to do that over multiple regions, also using things like on-demand and not only spot. So that should give you at least a good indicator of the scale. And it's really relevant for things like NLP modeling, where they need to churn through all of these documents. I forgot how many they had. 533,000 documents and 32 million words. So the goal here is, with all this unstructured text, to try and derive a topic for that and then classify all of these documents automatically.
Can I ask you something?
Yes?
Can you ask people in the audience how they would be able to use your service, just so I get a better understanding of the actual
Yes,
example?
I will. I'm actually moving up to the managed services, and that has a number of specific examples that I think, yeah, so it's a little in the weeds now, but yes. So, yeah, I talked about the ground truth in terms of how do you create that initial classification set, if you will. And one of the options here is what we call artificial intelligence, or human-based artificial intelligence. So Mechanical Turk is actually a service that lets anyone that's out there sign up as a worker and work against hits, or what are called human intelligence tasks. So there are a couple wrappers for this. Things like Label Me is one of them. But you can see there's a price that's paid for me to do things like tag things in an image. And I can do as many of these as I want. They're different projects. Most of them are open. In some cases, there'll be requirements. So you'll have to do an initial, essentially you're getting trained on the data set by classifying, say, a half dozen different images before you can actually start work against it. But this is what's getting used for things like, say, shape detection of trees, right, as a very obscure use case, if you will. But if we look at this just in terms of what is the type of use case, so you can see on the right-hand side, and I captured this from one of the projects that's, I think, up and running right now. So this is, I would surmise from what they're doing, that they're trying to do OCR for cash receipts, right? So the specific task here is that these are the receipts, and you are required to draw a bounding box around the receipt. Now, the use case there is that it's very hard and tedious for a machine or an ML algorithm to actually go and delete all of the other stuff around the company logo, for example. So by having people just tag these out, it allows the OCR system that's getting trained to get trained without any false positives. So very useful for those types of use cases. And you can see the population there. It's sort of, it swings, but the greener pieces are people that actually return and do more jobs on Mechanical Turk. Just in terms of demographics, when the service launched around, I think, 2010, 2009-ish, a lot of it was APAC-based, but oddly enough now, there are a lot of, I think about 75% of the workers are US-based. So it's people just in their spare time classifying things for different projects and getting paid for it. So very interesting use case. So moving up to managed AI services, and this is where we get to recognition, right? So recognition is basically what I described before packaged as a managed service. So there's a set of APIs you can use to consume it. And if you think about all the use cases that we talked about, like say, it doesn't do OCR yet, but OCR is one use case. Maybe facial analysis is another one. Maybe say celebrity recognition is another one. These are all different pipelines that you would have to build, based on that initial architecture I discussed. But they're nicely packaged up, right? So the other cool thing is that there are 5 of these now, but we continually add new, say, flavors or endpoints to the service. So celebrity recognition and image moderation were added over, say, the last year or so. But just to go through all of these and explain what they basically do, object and scene detection, you can pass in a photo or give a location to say a photo, an image, a JPEG, PNG that's sitting on S3 on Object Store, and have it classified for you. In about 500 milliseconds, it will return all of the objects in the scene. The important thing is that it classifies the objects, so things like chairs, flowers, tables, etc. But it also classifies other things too, like the actual scene. So the one on the left could return a label, I am 90% confident that this is indoors. The one on the right could be 90% confidence outdoors. And that's used by deep learning for things like detecting sky, et cetera, right? And then there's also a concept. So, if it were a photo of, say, this room here, the scene may be indoors, but the actual concept may be a meeting room, in addition to identifying things like people, chairs, et cetera. So facial analysis is a second one. And we often look at this and we go, okay, it's just detecting, matching faces, et cetera. But there are a number of, specifics here in terms of how recognition is doing it, in that we're able to identify, of course, there's a confidence score to all of this, right? So there's never 100%, there may be 100% accuracy on some things, but in most cases, it's a confidence score, and then you determine anything over 80 or 85%, that's okay, I'll take that label as fact. And you sort of have to tune the system for all these different endpoints for that. But demographic data, right, so 97% certainty that it's a male, right? There are facial landmarks that are identified, such as spectacles, mustache, et cetera. General attributes, and then things like image quality. And this is specifically, we look at this as a way to provide feedback where you can then tune the system and figure out what the right kind of photographic quality from a lighting and sharpness perspective should be in terms of what you're feeding the system. Because you always want to feed it optimum, say, images to get the best results. So there's also face comparison, and face comparison basically takes face A and face B, does a comparison, and returns a confidence score and similarity. So you can think of the use cases here, things like facial-based identification for authentication when entering a building using a camera. And because things like facial landmarks or facial features are detected, like, say, mustache, beard, different types of hairstyle, et cetera, or just a different hairstyle, it allows us still to get a confidence score across the same individual with different facial features. The other important thing is you can see that the faces are angled, right? So all of the landmarks in terms of top of eyebrow, side, tip of nose, side of mouth, shape, outline of the face, these are all stored as vectors. And it allows us, because we know where different aspects are of the face, right, in terms of the relationship between the eyes, the nose, the mouth, et cetera, to estimate what the tilt is, what the pitch, what the yaw is of the face, and then combine the two and get a more accurate comparison. So facial recognition, this goes one further, right? So I create an index. I then add items to a collection. I create a collection, and then I index photos against that of faces. I can have up to 1 million different faces in a collection, and then I can take an image and say, does this image appear anywhere in this collection? So one good example there is a Washington County Sheriff used this for mugshots and case files to try and identify things like cold cases, et cetera, and they've been doing it pretty successfully. The interesting thing here is that when you look at identifying or finding a face in this crowd of, say, 1 million images, we will return within, say, 1 second a hit or a miss. So it's not a lengthy processing period, right? So that allows use cases, for example, if it's law enforcement out in the field, to use cameras to take photos and get instant results back, as opposed to having to batch that up and do it later. So these are two, the other two things that I talked about that we added: celebrity recognition and image moderation. So because IMDb is a part of Amazon, we have access to all of those celebrity faces, right? So given that they are categoried, if you do recognize celebrities on faces in an image, we'll detect the faces and then try and figure out if it is a celebrity that is stored anywhere on IMDb. And then the interesting thing here is that the actual IMDb URL gets returned. So we've seen media customers like studios, for example, take clips or B-roll or A-roll or whatever that they're working on that they may have tagged in their metadata systems, actually run it through this recognize celebrities function, because sometimes whoever's doing the manual tagging misspells the actor's name, and then that clip gets lost if someone only searches specifically by name. And then the moderation labels, question? No? Sorry. The moderation labels allows you to basically detect explicit or suggestive content. So this is really useful for not only photos, but it could be user-generated content that gets uploaded, and it could be images, such as compared to Flickr, et cetera, where there's a lot of user-generated content. So you're able to pre-screen that before the user uploads it, for example, by making a call to recognition. And the other use case there is obviously for UGC video, right? So if you extracted a couple frames out of the video, ran it through recognition, you could try and determine what type of content the user is uploading, which makes it a lot faster to onboard new content as opposed to either retroactively doing it, which is not a good way to do it, or potentially have a whole bunch of people that have to screen all the content coming in. So if we combine all of these together, right, just for taking an image, we can detect objects in the scene. We can detect if it's IMDb, right? We can detect the name of, say, an actor. We can detect things like demographics, age range, appears to be happy, not wearing eyeglasses, et cetera. So this is sentiment detection. So we try and, by the facial features, estimate if the person is happy, frowning, et cetera, upset, and so forth. There's a moderation level that I talked about, so the moderation level is safe for this. And then if you're looking at this in combination for video, if we're detecting, say, a person by facial comparison, we could then potentially look across a video stream and then extract where they are appearing in that stream. So one interesting example here is C-SPAN. When we launched recognition, they built this out in 3 weeks. They basically took 99,000 people. So if you think an image or multiple images of every politician up at the Hill, right, created the index in 1 day by indexing all of those images in face collections. And that saved them about 9,000 hours a year of a manual curation, which is pretty large. And just in terms of the, so if you go to C-SPAN and you see, you watch C-SPAN 135, whatever it may be, a lot of the VOD clips, everything that appears below it has been ID'd through this type of workflow. So from an actual architecture perspective, it's mostly coupling existing on-prem processing with now a new way of augmenting the data on AWS, right? So the existing coders on the right-hand side are now additionally extracting things like stills. Those are then fed into an S3 bucket object store. And as these arrive, you can have S3 generate an event for each one, which generates a trigger. They have an instance that they run, and this is to do a differential comparison against the last frame. And that's because C-SPAN, nothing much happens, only every now and again. So it's usually the same person for a long period of time. So that basically relieves them of having to make multiple API calls for potentially the same person. So just final thoughts. I think the key takeaways here are running deep learning or these types of infrastructures. It is hard, but it's really hard if you want to do those niche use cases. And the thing to remember there, or at least what we see customers doing, is they'll adopt the managed services to, say, eliminate 80% of the problem, and then they'll take their engineering, their DevOps, their deep learning, their data scientists, and focus that on the other 20%, which actually differentiates their business. So that's the one thing that we call at AWS, we call this undifferentiated heavy lifting. So if you have a managed service for deep learning or AI or ML that solves 80% of the problem, utilize it because we are continuously training that and having it operate at scale. It's very hard to do something like this if you did it yourself and have it run cost effectively and say return a hit on an image in 500 milliseconds or return all faces, match against all faces in a million face collection in about a second. And then there are these other tools. So if you have to do the other 20%, right, the real key things for these types of workflows, if you will, are I talked about Lambda, like serverless compute to glue things together at real low cost. But when you have to do the heavy lifting, then the storage is S3. So all of your image, your data sets, everything, and that can be encrypted because it's potentially also intellectual property. And then the fractional billing, so that benefit you get from the compute and the storage using Spot as a way to reduce cost for processing over a lengthy period of time. And I'll just wrap it up with this one. So Marinus Analytics, they utilize recognition as well. And the reason I put this in here is a lot of these use cases are, that's great, but is it actually doing anything for humanity, right? So their use case is actually for human trafficking. So they do things like, say, scan social media networks. They work in combination with law enforcement. And basically, it's used to stop and prevent and identify human trafficking on social networks, which apparently is a real problem. With that, I'll say thank you. And I have about, how much time do I have? 12 minutes? Enough for a demo. So give me 1 second. Yep, that's legible. So this is a FPGA-based instance in US East in Amazon that I spun up. And this is a partner we have called Mipsology. They make an ARMY that's tailored for FPGA called Zebra. And basically what Zebra does is it exposes things like CafeNet, MXNet, which are open. And then it allows you to use the FPGA as a target instead of a GPU. So the benefit of an FPGA is that the inference rate, in other words, identifying everything in a frame, can be exponentially greater times faster, right, than, say, using a GPU. So the problem is you sort of have to compare the power consumption that you have on a GPU versus the low power and high speed on an FPGA. There is a disadvantage in that you have to actually use the development tools to produce the image to run on an FPGA, and that is always intellectual property. So for this specific reason, we have an internal repository that anyone that develops what we call an AFI or a firmware image for FPGAs is stored where no user can access it. So I have the ability through and I'll just go in here now. You just log in and I'll show you. So I've already prepared everything here, but essentially what this is doing is once it spins up, you can see here it's detected the FPGA board. Now it's basically running batches against that. So this is actually building the deep neural network, right? That deep learning network. All the different layers are getting loaded. And now it's going through batches. And what I'll do is I'll just go back through here. So essentially what this is doing, as you can see it classifying things here. This is using, I believe it's using AlexNet, which every year there's a competition to see who can improve to the greatest extent these deep learning algorithms. And it gets awarded to it could be a university every year. So AlexNet is one of the popular models, if you will, that is utilized here in combination with CafeNet against the FPGA. there's delay, and the delay here is that the browser can't keep up with the amount of images coming back. So you can see up at the top there, the processing rate is, I'm handing it batches of 1,300 images every time it fulfills all the requests, and then it's classifying everything. So you can see, combination lock is, has a classification, right? Or the type of terrier in that picture, or a chest. And those are getting identified at a rate of about 959 images per second. Now, the use case here that you can think of many, right? But bear in mind, this is unoptimized. It's in debug mode. So essentially, if this were not to run in debug mode and were to be optimized, you'd hit about 2,000 frames a second. So the real use case here is if you can classify everything. This model is for classifying objects. What if you're classifying people's faces? What if you're classifying, say, NLP at the same time? And the NLP is based on closed captions. You can now look at use cases where, say, you feed every network, every news network in the US. Maybe it's all the major ones, say 12 of them running at 30 frames a second, and you're extracting real-time political sentiment as the algorithm runs on a single instance. The thing is, what do you do with the data, right? So this is where we have other services like Kinesis for actually streaming data in and then inspecting as it goes through. So you could say, take all of this data and push it into a Kinesis stream, which then gets sharded out as you need more capacity, and then inspect it periodically. So you could use things like, say, tallies, right? Or you could do facial expressions or, say, sentiment analysis. So it's very interesting from that perspective. I have one other demo, and then I'll go for questions. So let me just pull up recognition. So on the AWS console, if you have an account and you log in and you go to recognition, there are a number of pre-canned demos. But essentially, the one thing I wanted to talk about here is just that these are all the things that we talked about. So for example, here this is doing moderation, no labels detected, and it's safe to view the content, right? The same for facial analysis. You can see here that the tilt, pitch, yaw that I talked about is identified. Also, the other thing that's important here is that we don't look at images by pixel dimensions. We look at it by fractional positional dimensions. So this means that if you feed different resolution images, one could be a mugshot, the other one could be a low resolution, say, security camera capture. We aren't going to look at the pixel boundaries to do things like calculate the left and right eye and the distance between them. So that's really important for facial matching. And you can see some of the things returned, like estimated age range of the individual. Celebrity recognition, identify, and then that goes back to IMDb. And then face comparison is the other one. So the interesting thing here is that I've run this through, say, historical data. So I have one of the, I think, original mugshots that was taken of Joseph Lennon, right? And it's very bad quality. It's a front and a side perspective view. And then one of the later portraits that he had, and that's still an 80% match between the two, even given the degradation in quality, different facial features like beard in one and not in the other, etc. But this is where to go. I'll be around after this as well if anyone has questions, and I'll take questions now too. Yes. Yeah, so you would need something that so the problem here is Café, as it is now on this particular instance, looks at individual frames. So you could look at, this is something where Sean talked about reference architectures earlier in another session, but we get tasked with building reference architectures to solve these problems. So the one avenue we're looking at now is taking FFmpeg, extracting the frame buffer, putting that somewhere that I can then feed it into Caffe and do recognition against that. So then that lets me pull, say, an RTMP stream and feed the frames, for example, into CaffeNet onto the FPGA. No, it's, yeah. So it runs 2,000 frames a second reading individual images off of disk. So there's absolutely no optimization there for, say, an in-memory buffer of frames. Any other questions?
Where does this capability sit as compared to the FBI's?
I don't know.
They must have talked to you about this.
Not me specifically. Yeah, that's something. Yeah, I know they should be. But like I said, the Washington County Sheriff, so their existing system it's got Cold Fusion, PHP, etc. So really, almost legacy, but it is, that's given the amount of, scrutiny, security, etc. That is what those systems are, right? But essentially what they did is they took their on-prem mugshot database, they took only the front-facing profile of suspects and fed that into recognition, into a face collection. And then the coupling in terms of how do the law enforcement folks in the field actually use it, they build an application on a mobile device. So instead of having to figure out, well, we need to get these VHS tapes or whatnot off a security rig and then ingest it, and they could just take a photo in the field and it would return them results on that. So I know they've closed a bunch of stuff. The big thing that we did in the last couple weeks at least is we introduced this like almost deterministic match. So when you do you look for a face in a million in a collection of a million, it will consistently return it within 1 second. So now they're actually able to, that was big for them because now they can process more suspect images through that at a higher rate, if you will. Any other questions? Man.
Could you feed it data sets that aren't necessarily image-based? I mean, what we say network conditions, so you can recognize certain network conditions.
Yeah. So for those types of use cases, deep learning also covers things like natural language processing or topic modeling or whatnot. It's not only for images, but there's also ML as a service, right? So those types of things you're talking about, a lot of customers will use the different ML models. And the input there, you can almost think of that as a CSV that defines these are my known quantities that are valid. Give me things that are outside of this boundary, right? Or fall into this. And this goes for things like, say, recommend me a genre of movie, based on ML. The differential that ML gives you over just writing code and doing a bunch of if-then-elses is that I can easily recommend a movie based on what I've watched. But what if I want to widen that scope? And that's something you can't do with, say, table selects in a relational database.
How does the pricing work for the ML models that you guys do have?
So there's no pricing for the models. There's pricing for consumption of the service. Where is that? Let me try. I'll find that and get with you afterwards. It's buried here somewhere. Any other questions? Yes?
Do you have any stories about using deep learning for sort of non-standard business cases? I mean, image recognition is a really popular one, facial recognition, obviously, but does anybody use it for food or?
Yes. So there are actually a lot of papers. So the question was around non-standard use cases versus just, say, identifying objects. There are a number of papers, and a lot of these get published at, for example, SIGGRAPH every year, right? And they're all public as well. But some of the interesting ones that I've seen are things like fashion topic modeling. So the idea there is that given an image, I can determine what the genre of fashion is that the model is wearing. So there's a deep neural network that's trained specifically to identify, if you think about the facial features I talked about, this one is trained to identify landmarks being the outside shape of clothing, and then determine that this is a top, these are pants, this is a belt, and then classify each one of those against a database using computer vision. So that one's interesting. Yeah, there are a bunch of interesting use cases in that area. Any other? Yes?
There's an interesting set of articles recently about IBM's use of a physics model for wave prediction at Monterey Bay and how they managed to accelerate it to 12,000% by basically using the physics model to train
Oh, really?
the ML model. And I'm wondering if you guys have looked at anything like that, because it seems like, for designing jet engines or something with the compute power you have, that would be stupendous.
Yeah, somewhat unrelated to machine learning, we do have a number of customers that do things like flow modeling for environmental, et cetera, right? But a lot of those types of workloads are purpose-built to, in some cases, run on top of a GPU on Windows. So at least their challenge there is to be able to spin up workstations and then orchestrate those, as opposed to be able to do this non-interactively. And those are some of the use cases I've seen there. Yeah, interested to talk about that afterwards. Any other questions? Yeah.
One other question. If you've got clients who are scanning social media networks to build their, what's the term you use there? Maps, they use it, learn
Yeah.
the source data. Presumably there's not, if you've got sort of 10 clients, it's going to be repetition of people.
Yes. So the question was around, I guess if you have a small set of data, how do you ensure that your network is not returning what it already knows, right?
Yeah, well, multiply. If you've got client A and client B and somebody's just scanned Facebook, then can you share as Amazon the data they've derived
No.
from Facebook?
No. So everything that we return objects on, none of the data, the image data is stored. So you can secure and encrypt that in your own S3 bucket. If you use KMS, it's encrypted for your account, and then the service utilizes that. The other thing is you can encrypt it with your own keys that no one else can read it, and you provide it to the service through something like Lambda. The things like the facial data, like if it's creating a collection, only the vectors are stored. So in other words, my facial characteristics. It's up to you to actually then say, when recognition returns you I have stored this and here's the ID, the API call actually has to have a back reference to say that image that you have stored on-prem. So for things like mugshot databases, that's essential, right? Because no one could determine a person's face by just looking at a vector, by the data points. It would be a waste of time because there are too many maybe false positives, right? But protecting the image data, like for example, Washington County Sheriff, right? They keep that all on-prem, and the back references say a UUID or a hash that references one of those suspects' images or database records. So that way, if they had some problem in AWS where someone internally, say fudged the firewall rule, et cetera, there's no way for that data to be of any use, if you will. Any other questions? Nope. Thanks.